Good morning and welcome to this session, this special session on astronomy. This is actually triggered by some questions from some of you guys, and it's related to the homework, the last homework that you guys have assigned. Apparently it has a little bit of work, and so I'm going to go briefly through the homework. If you have any questions, specific questions about the problems, please let me know. So let me share the screen with you guys. Share. This is the problems. These are the problems that we have to work out. The problems are, as you can clearly see, are from pages 161, 2 of them. From pages 167, there are 2 of them. And from pages 176, there are 2 of them. This concern the units 22, 23, 24, and 25. On light, basically, and how light is used to study the universe and how it's used actually in astronomy. Let me stop sharing this screen and share with you my notes. I hope by now that you have a piece of paper and you also have the book open, or at least the Canvas session open to follow with me so that you can do the calculations and don't have with it. Don't have a problems with it. I'm not going to go in details about these problems, but hopefully enough so that you can finish the calculations. Problem 11 from page 161 says a typical frequency used for cell phone communication is 800 megahertz. So the frequency in this case, I know in this book, the frequency is used for the letter nu. You can use the letter nu if you like, or the letter F, whichever you feel comfortable with. Both of them refer to the same thing, frequency. So the frequency is given, and it says it's 800 megahertz. Just a reminder that a mega stands for 10 to the power 6. So technically, this is 800 times 10 to the power 6, or if you like, 8 times 10 to the power 8 hertz, because 100 is 10 to the power 2. It's the same thing. This is the frequency it was given. What is the wavelength? For that, we're going to use the dispersion law. We know that the frequency times the wavelength must be equal to the speed of light. This is the dispersion law. Obviously, we are given the frequency. We know the speed of light, which is 3 times 10 to the power 8 meter per second. By the way, the hertz also, if you guys remember, is the same thing as 1 over second. It's the same thing in terms of the units. It's just in honor of Mr. Hertz that we call it hertz. It's 1 over second. It's not a fundamental unit, the hertz. In other words, it's a derived unit. It's the inverse of one of the fundamental units. From here, obviously, we can calculate what the lambda is, and lambda turned out to be a very simple thing in here in this case, which is 3 times 10 to the power 8 meter per second divided by the frequency nu, and nu in this case is 8 times 10 to the power 8. 1 over second, again, I can write it 1 over second. It's the same thing as I was saying, hertz. Cancel the second with the second. Cancel the 10 to the power 8 to the 10 to the power 8, and that's important. So when you're doing calculations, don't punch in the calculator yet until you're done. So at this point, it's going to turn out to be 3 over 8 meters, okay? Slightly less than 50 centimeters. That's the wavelength used for your cell phone. So if this is 1 meter, this is about 1 meter, we're talking about this much. That's a wavelength, okay? How does the wavelength compare to the size of the cell phone? Again, I just gave you the, if this is the wavelength, the cell phone probably is this much. It's about twice the cell phone basically length. So a wire inside of it, which represents the antenna, must be wrapped around, okay? Or something like the the edge of it must have that antenna that has to at least be in this length to be in resonance with the signal. Or if it's a dipolar antenna, in this case, it's just only need is 25 centimeter, which is slightly longer than the, probably about twice as long as the typical cell phone. Again, this stuff is, once you find an answer, it's going to be slightly less than, so when you do the calculation, it's going to be what? Not 50 centimeters, 50 centimeters is 4/8. Finish the numbers and do the discussion accordingly. If you need to take your cell phone and measure its size and see from end to end, the longest side, how big it is, and see, okay? But again, your cell phone might have a different thing in here. Okay, I went too far in this problem. I really didn't mean to do that. Okay. The next problem, 14 from 161. It says, what is the wavelength of a photon that has 1,000 times as much energy as a photon with the wavelength of 500 nanometers? You guys remember when we studied the spectrum of the electromagnetic radiation, we saw that the visible light lies between 700 nanometers and just about maybe 400 nanometers. And this is a 500 nanometer. 500 nanometer is actually the blue light. So it's in here. Anything above the red, you cannot see it with your eyes. Anything below the violet, you cannot see it with your own eyes. There's more energy. And as a matter of fact, we saw that the energy is proportional to the frequency, where h is just a number, is a constant, okay? Or inversely proportional to the wavelength, it's the same thing, hc over lambda. Because of this relationship, we can replace nu as being c over lambda, the frequency. So that's why I can write it this way. So if the energy is 1,000 times that of the 500 wavelength, this is a 500 nanometer wavelength, then in this case, the wavelength must be 1,000th less. So the wavelength need to be 1,000th less than that of the 500 nanometer. The 500 nanometer is exactly 500 nanometers. By the way, a nanometer, a nano is 10 to the negative 9. These prefixes, they come in handy when you're doing these calculations. But we're not going to convert it. We're going to leave it as is, okay? Leave it in nanometers. It's no big deal. Divided by 1,000. So that gives me the answer should be 0.5 nanometer. If you really care, you could find the frequency in here for the 500 nanometers by dividing c, which is 3 times 10 to the power 8 divided by 500 nanometer. Don't forget that nanometer is 10 to the power negative 9 meters. And you find the frequency, and then find the energy, and then you multiply that energy by 1,000, and you solve for lambda, and you should find the same answer, which is half a nanometer. Half nanometer is extremely short. Extremely short. The size of the atom is about half an angstrom, or 0.5 10 to the negative 10 meters. This is 0.5 10 to the negative 9, or 5 times 10 to the negative 10 meters. This is about 10 times bigger than the hydrogen atom. So this is the wavelength. So count 10 of them. I don't know how many I did, but 10 of them is the wavelength of this. So this wavelength is about 10 times the size of the hydrogen atom. Okay. I should be careful in here in stating this because I took the radius. I really should take the diameter, and the diameter is about 1 angstrom, okay? 10 to the negative 10 meters. In that case, my assessment is incorrect because it's going to be just 5 of them. 5 hydrogen atoms from diameter to diameter. I took the radius. I should not have done that. But if you take 5 atoms of hydrogen and line up one next to one another, this is the wavelength. But it's a very short wavelength. What is the spectrum again? Okay, this is 400 nanometer, and this is half a nanometer. Half a nanometer. So It's going to be somewhere in here, half a nanometer. Of course, it's far more energy. It's in the UV range. And this is a very, very high energy radiation. And it asks you later on, it says, okay, what it would be dangerous to be exposed to 1,000,000 photons of wavelength 500 nanometers, or 1,000 photons with 1,000 times the energy, 1,000 of these ones. Of course, each one of them is 1,000 times more energetic. So they end up basically with the same number, 1,000,000 times the million. So at the end, you're going to end up with 1,000 times 1,000, which is 1,000,000. So in terms of the joules, yes, it is the same amount of joules. But in terms of energy damage, would it be more dangerous? Obviously, it's going to be more dangerous to be exposed to the UV radiation because of another effect, the photoelectric effect. This will be high energetic ones that can cause cancer. Basically, they interact really with the skin and they can cause all kinds of problems. So yes, this is more dangerous, okay? Not necessarily the photoelectric effect, but does give us an insight into the fact that the energy is proportional to the frequency, and the higher the frequency in this case, it's going to be 1,000 times more frequency, because it's 1,000 times more energy. H is a constant, by the way. H just a number, 6.626, 10 to the negative 34 joules second. So the higher the frequency, the higher the energy. Since the energy is 1,000 times more, frequency is 1,000 times more, the wavelength is 1,000 times less. Okay? So basically that is in a nutshell what the whole thing is. So yes, it's more dangerous because you are in the UV region, getting closer to the X-ray region, which is really highly energetic and can cause a lot of damage. So if you go and get exposed to the X-ray radiation for X-ray chest, for example, or something that has to do with the bones, usually they don't expose the skin or the person for a long time for the X-ray radiation, just to get the reading and their exposure, and then that's it. Because if you expose them for a long time, you're going to get into, you're going to damage the cells, and that you don't want that, okay? Anyway, so this is hopefully an explanation enough, and you can read more about it and post in your answers. By measuring relic radiation, I'm looking at problem 12 from 167. Okay, by measuring the relic radiation left over from the Big Bang, astronomers have measured the wavelength, have measured the average temperature of the universe to be T equals to 2.73 Kelvin. Okay, at what wavelength does this background radiation emit most strongly? What part of the electromagnetic does this wavelength? Okay, I'm going to look briefly in here because you guys really need to have the book open with you guys. I'm looking at the 6th edition, but it should be the same thing on the. It has to do with the not the dual nature. No, not chapter 21. What am I looking for? Chapter 1. It has to do with chapter 23. In chapter 23, there is the displacement law, Wien's displacement law, the one from page 165. Okay, so it says lambda, the wavelength. This is the max wavelength. Okay, not any other wavelength. So this is the question basically to answer it, because the spectrum is going to be spread for a given temperature in what looks like almost a bell curve, like this. Okay, so this is the lambda max. This is where the maximum wavelength is going to be emitted for a given temperature T, and this is obviously inversely proportional to the temperature, and the formula is 2.9 times 10 to the power 6, and in here the units. Okay, because we have a Kelvin downstairs, so this is a temperature in Kelvin, exactly how it is in here. So we need a Kelvin. Since it's in lambda, it has to be in nanometers. Okay, so the wavelength is measured in nanometers for this formula. Don't be confused. Don't use a meter for this formula in here. The displacement law for Wien's. Okay, use this in nanometers. So you have everything for this problem. 2.9 divided by 2.7 is going to be about 1,000 I mean, a million nanometers, basically. Remember, a nanometer is 10 to the negative 9 meters. So it's going to be a million. I didn't do the math in here. You have to really finish this number in here. It's going to be slightly more than this number, but you're going to finish it. So it's going to be about 1,000. I'm sorry, not a thousandth, or 10 to the negative 3 meters. In other words, it's of the order of a millimeter. Millimeter. Okay, that's what so slightly more than a millimeter. So that's the answer to the problem. What part of the electromagnetic spectrum is? So it's going to be way outside of the what is the spectrum I drew earlier? I mean, we can do it again. Lost in here. Here. So it's going to be, it's not a nanometer, it's not a micrometer, it's of the order of a millimeter. Okay, so that should put it in the infrared region, probably the boundary between the infrared and the microwave when you look at the spectrum from page. And again, all of this from page 159 from the 6th edition. This page. Okay. So hopefully you can go through these calculations and find the exact number in here. So I just gave it an order of magnitude so you can find the correct one. Because 6 minus 9 is minus 3. And 10 to the negative 3 meters is a millimeter. Okay. But you have to find the number in here. 2.9 divided by 2.73, which is slightly more than 1. And then refer to this electromagnetic spectrum to find that it should be right at the boundary between the infrared and the microwave. And it's not visible, of course. You cannot see it with your eye. It's too short of a wavelength, extremely low energy. 15 from 167. Problem 15 from 167. Okay, what is the ratio of luminosity per square meter coming from a part of the sun that is at 5,800 Kelvin versus that of at 5,000 Kelvin? For that, we're going to use the Boltzmann Stefan Law. Boltzmann Stefan Law give us this basically luminosity per square meter. So it's going to be actually the energy per meter squared is proportional to the temperature to the power 4. For the sun, for the regular sun, okay, let's use the symbol. It's going to be sigma times 5,800 Kelvin to the power 4, because they tell us the sun emits us around that temperature. And for a sunspot, it's going to be the same formula, but instead of 5,800, we have 5,000 Kelvin, a lot cooler. So in this case, the ratio of the two, you can just do the math in here, sigma times. That's why it's a good idea not to carry out the calculations, because the question was not asking you for the luminosity per unit area. It was asking you for the ratio of the two regions of the sun. So don't calculate either of them. You could. Sigma has a given value in there, has a 10 to the negative 8 times. Okay. 5.67 10 to the negative 8. Okay. But don't do the calculation. Don't even calculate that. Just calculate the ratio, because sigma will cancel out. Boltzmann Stefan constants will cancel out. So there is no need to look it up. Okay. There is no need to find it. As a matter of fact, you can go further than that, because the ratio of the powers is the same power of the ratios, because both of them are to the power 4. So in this case, and then you have a lot of simplification. So before punching the calculator, do your simplifications. The zeros cancel from the top to the bottom. As a matter of fact, there is another 0 that is going to cancel, because I can move the decimal points in here just by doing the ratio of 5.8 over 5 10 to the power 4. As a matter of fact, I can even simplify this one further by doing, again, at this point, you're ready for calculator. You don't want to listen to me for the rest of the one if you're not really algebra-minded person. But if you are, it's easy actually to do this one much easier than that. Multiply by 2 in here and multiply by 2 here. Again, if you don't care about this step, ignore it. Just do 5.8 over 5 to the power 4. Or if you don't want to do that, you can actually take this one, 5,800 over 5,000, and do the ratio and take it to the power 4. Or calculate this, basically luminosities per unit area, and this luminosity per unit area, plug in the value of sigma, which is 5.67, 10 to the negative 8. One of you guys who communicated with me, so it's going to be in watts per meter squared, and by Kelvin to the power 4. Okay, anyway, this is not the standard deviation from your statistics class, okay? Sigma has so many symbols used in all kinds of physics, so this is a different one. This is Boltzmann Stefan constant, okay? So at the end, the ratio is going to end up with this number. So if I multiply 2 by 5, that's 10. And if I multiply 2 times 5.8, it's going to be what? 16, 10 plus 1, that's 11. So it's going to be 11.6 divided by 10 to the power 4. The reason why this is easy is because like any number I divide by 10, is all I have to do is displace the units. So it's much easier for me to put 1.16 to the power 4. You will see that it's going to be about twice as much as more luminous than the dark spots. That's why they appear dark, okay? Twice as luminous as those sunspots, which should appear darker than the rest of the sun. Okay? So that is 15 from 167, 14 from 176. Okay? Using the formula for the hydrogen energy levels, calculate the energy of a photon emitted when hydrogen goes from level 143 to 142, okay? So in this case, it's going to be an emission spectrum. So we're going from remember, from n equals to 1, 2, and so on and so forth. We reach it 142 and 143. And we're transitioning from here. So in this case, we're going to emit energy. The difference in energy is going to be an emission in this case. So this energy, which is going to be h times the frequency, and this is the frequency we're going to be measuring, or hc over lambda, and that's the lambda we're going to be measuring. Okay, so that's basically what this problem is. Remember, I'm looking at the pages in here. Formula for this one is on page 169 from unit 24. And it gives you the energy given for a specific energy level, negative 2.180, 10 to the negative 18 joules divided by n squared, where n is this number. Don't forget to square it though. Okay? Here is the deal with this problem. I mean, it's common for chemists and physicists to remember a different version of this one, which is negative 13.6 electron volt per n squared. Electron volt and the joule are the same unit. Actually, the book discusses this point in here. They are both units of energy, where 1 electron volt is 1.602 10 to the negative 19 joules. It's basically the electron charge times the volts, 1 volt, okay? So that is basically the same formula. Physicists and chemists remember this formula in here because it's much easier to have no power than this one by just making this conversion. So negative 13.6 electron volt is a well-known value for the hydrogen atom. Okay, and that's, I think, what I used in my notes in the lecture. This video is getting longer than what I was hoping to. But anyway, so let's calculate E141 and 142, which is going to be negative 2.180, 10 to the negative 18 joules divided by 142 squared. And E143, 143, not the 134, is negative 2.180, 10 to the negative 18 joules per 143 squared. Okay, some of you are bothered with the 0 that I've been carrying because it's after the decimal points. And those are, again, the math-minded people. But we're doing physical astronomy, basically, and in physics and chemistry and astronomy, and in science in general, regardless of what field of science, sig figs matter. Significant figures matter. That means we know this answer up to this significant figure. We have 4 significant figures. We know the 2 exists, we know the 1 exists, we know the 8 exists, and we know the 0 for sure. We're not sure about anything else. That's why we keep on the 0 in here. So when we do the calculation, we have to take that into account because it's going to be a very tiny number. So basically at the end, since we ended up in 142, we're going to do 142 minus 143 basically. So the energy that we're talking about in here is E of 142 minus E of 143, and the answer should be negative. Basically, here is the trick with this one. Either you do the calculations and do the calculations and find the difference between them, and it's going to be an extremely tiny answer. It's going to be of the order of 10 to the negative 24 joules. Extremely small number, okay? So this problem has more parts in it. What is the wavelength? So once we find the energy, we're going to equate this one. So this finish yourselves. And then once you find that, you're going to say this is hc over lambda. And from here, you're going to find the wavelength as being hc over E, where E is this number. So you plug in this number in this formula. You have H, which is 6.626 10 to the negative 34 joule second. And you have C, which is 3 times 10 to the power 8 meter per second. And you have everything, so you should be able to find the wavelength. And once you find the wavelength, it should be a very big value in meters compared to the nanometers, for example, the visible light. It's going to lie somewhere in the order of a centimeter. It's going to be even longer than the wavelength that we found earlier, which was of the order of a millimeter, if you guys remember somewhere here from one of the previous problems. Problem 12 from 167 was of the order of millimeter. This is going to be even longer. It's going to be of the order of a centimeter. So this should put it right smack in the microwave region. So I'm talking about problem 14 from 176. So this should be of the order of a centimeter. Okay, so and that should be the microwave region. Again, refer to the previous picture for the spectrum from unit 22. And that's on page 159. And you will see that it's going to be of the order of the microwave. It's going to of the order of centimeter, just between the police and the cell phones, basically signals, radar technology. Last problem in here, and that is problem 15 from 176. And it's explain the meaning of the transition from the hydrogen from n equals to 1 to n equals to infinity. So you have a hydrogen atom, here is a nucleus, here is n equals to 1. Here is n equals to 2, and so on and so forth until n equals to 1,000,000, if you like. But you're not sticking in here, so n is going to end up in infinity. That means the electron is free. So a transition from n equals to 1, where the electron is bound to the ground state, for the hydrogen atom, of course, to infinity, that means the electron is free now. It's not bound to the hydrogen atom anymore. And you end up, of course, with the hydrogen atom just being the nucleus in this case, the proton by itself. So in this case, it's an ionized hydrogen atom. So this, what this means is this is an ionization of hydrogen. That's it. So you go from hydrogen to H plus an electron free by itself to move somewhere else. So this is what this means. Okay, and calculate the energy associated with this one. Okay, we're going to use this formula again here to calculate that. And they tell you in between parentheses, recall that anything divided by an infinite number can be treated as 0. Because you're going to divide by a huge number, you're going to end up with a very tiny number. So you're going to use this formula. I prefer this one for this particular case, okay? You can use the joules if you like, but it's easier to handle because you don't have to carry this many powers. But if you like to, you can use this one in here. You can use this one at the end, convert back using this conversion factor, or you can use this one from the get-go and be done with it. But you're going to be carrying so many powers. So for E1, we're going from 1. So n equals to 1. The energy is simply equal to negative 13.6 divided by 1 squared. Remember, this is an electron volt. 1 squared is just 1. So the negative 13.6 divided by 1 is just negative 13.6 electron volt. Okay. E infinity, again, you're going to divide this one by a huge number. I cannot really write infinity in here because it's a limit. It's not really a huge number. It's going to be 0. That's what the note there says. Okay. And the transition then is going to emit energy in this case, and that emitted energy is going to be 0. That's the final energy, this one. This is E at infinity minus E at 1, which is this number, negative 13.6. Negative times negative is positive, and the energy in this case released in the form of radiation is 13.6 electron volts, or if you wish, 2.18 10 to the power 18 joules. Okay, it's the same thing. So the energy at the end is 2.180 10 to the power negative 18 joules. Okay, so the point being in here is this is how much the energy is. So this energy and the numerator really, it represents the energy of ionization of the hydrogen. 13.6 is the energy of ionization for the hydrogen. Okay, so this is all of the homework problems. And I think at this point, it's a good place to stop at. If you have any difficulty, please let me know. Thank you.